Welcome to BEZ Talk with thought leaders in application of modeling for performance management capacity planning. Today's our guest is Dr. Andrew Bondi, and Andrew is recognized expert in application of modeling for performance engineering. He has a lot of experience in application of modeling for IT and optimization of business processes. His recently published book, he recognized he has Michelson Award, and today we'll ask Andrew several questions about role of modeling, application of modeling for performance engineering. We ask him what is the difference between performance engineering and software performance engineering, application performance engineering and software performance engineering. We'll ask him what his predictions, what will happen with modeling and capacity management during the next 3-5 years. We're at CMG 2017, and let me introduce our guest, Andrew Bondi. And Andrew is a well-known expert in modeling. He recently published his book on Foundation of Software System Performance Engineering. And one of the questions is, what is the difference between systems and software performance engineering? This is titled your book. So
Right. In principle, not really all that much. In fact, the book makes no reference to systems outside the domain of computers in any case. But I put the word systems in there because I wanted to emphasize that we model the way components interact with each other and the impact that that has on performance, and also the impact and interaction between the computer system that controls a mechanical system or an embedded system of some kind. At the time I wrote the book, I was working on fire alarms, and I was interested in the performance requirements of alarms and how they work. And the alarm is triggered by a computer system, and the performance requirements were driven by the needs of the system that was being controlled by the computer system. So hence the term Foundations of Software and Systems Performance Engineering.
Okay. So what is the component of, what is the distinction between software performance engineering and system performance engineering? So,
in terms of techniques, the techniques that are involved, none.
Okay.
The main difference arises from where you get the information about how the system is going to behave.
Okay.
But since everything is controlled and monitored by computer systems these days, the difference is really
So this is performance.
rather fuzzy.
This is performance engineering. But what is the role of modeling in performance engineering?
I think it depends on the local practice. From what I've seen, the role of modeling nowadays is to quantify demand and engage in sizing exercises,
Okay.
but also understand how scheduling disciplines are going to impact both throughput and response times. So for instance, if you have priority scheduling, you want to make sure that the high priority jobs are not going to starve out the low priority jobs. But you can also use an understanding of priority queuing to understand how changes in the nature of the traffic and the nature of the workload are going to affect what priority scheduling mechanism you should have. When the web was introduced in the late 1990s, a paper came out that described how giving priority to incoming packets in order to preserve the buffer space didn't actually work very well in a system with traffic that was so heavy that the TCP connections would time out and there'd have to be retransmissions.
Okay.
The only way to ensure a timely retransmission in this context was to make sure that there was priority handling in the CPU for the transmission of acknowledgements, so that the system at the other end wouldn't time out and retransmit, because you'd have a vicious cycle if you did that. So there, an understanding of priority queuing modeling, I suspect, informed the authors of that paper about how scheduling should be done. So the change in the nature of the workload affected the policy that was most applicable in that context.
Okay. So when we talk about priorities, concurrency, we're talking about different workloads and applications. So do you have distinction in your mind between software and applications performance engineering? Your book called about system and software performance engineering.
Right.
But application actually controlled by software.
Mm-hmm.
So what is... we're talking about application performance engineering, is it right?
I guess one could talk about it in terms of application performance engineering, but I find that the distinction is not helpful for a number of reasons. Historically, performance evaluation, as it was initially called, was pioneered by people with training in operations research, because computer systems were quite new. The first queuing network model that could be solved efficiently, describing a cyclic system, was actually developed in the 1950s by Ernest Königsberg to describe the movement of wagons containing coal, which cycled around the mine in and out. And that was the first product form, closed queuing network model. And then the next product form, closed queuing network model that could be solved efficiently, was Jeff Bouzin's closed queuing network model, about which you probably talked in a film that you made about Jeff Bouzin in this series.
Sure. Yes.
So.
Okay. So but what is the role of modeling in all this process of making decisions about priorities and managing software?
I can think of two things right away. One is that an understanding of modeling and of the conservation principles that modeling tells us about can be used to inform an appropriate design choice that keeps you from bringing a system into deadlock, for example, or identifying the conditions under which a system might go into deadlock. A long time ago, modeling was used for capacity planning. Right now, I focus on very simple models to size the number, for instance, the number of connectors that you have to have between a database and an application server, for example, or between the load balancing server and the application, and the application servers are on the access side of the load balancing server. Because if the number of channels is too small, you introduce a software bottleneck that prevents work from getting inside the system, and the main symptom of that is increasing response times, both over time and with load, while having very low resource utilizations in the system that's under test.
Andrew, when we talk about modeling, and we try to answer very specific what-if questions using models based on measurement data, we address what-if questions, but our ultimate goal, is to make a decision. What do you envision? What will be evolution of modeling in all decision support systems to help to use modeling results to justify decision? Let's change priority, or we need additional 2 nodes. Okay, so how to go from modeling to the recommendation?
I am actually rather reluctant to mechanize this process for anything other than sizing, because I think the consequences of changes in system behavior need to be understood. I think and examples of changes in system behavior would be the priority inversion example, with the introduction of the web that I just described to you. And my main use of modeling right now is as you say, with design choices and with sizing choices, and where to deploy various kinds of activities. So for instance, when people talk about big data right now, they're asking the question, Should I do the computation close to the data, or should I move the data to the computation? Or should I move the data to the computation, or the computation to the data?
Okay.
And the answer is, it depends, and you answer that question with a model based on various assumptions about what you're doing. Now the volumes of data are so large that you have to move the computation to the data, with the expectation or the implied assumption that the output of the computation generates a lot less data than you were processing to start with.
Okay. And you have years and years experience in building and applying different type of models. What do you think will happen with modeling and the role of modeling during the next 3-5 years?
Curiosity.
Okay.
Curiosity. Curiosity about whether a design decision makes sense. Curiosity about whether changes in the values of certain parameters, such as the amount of data that's involved in a computation, the amount of time that a computation takes, the processing resources, the architecture of the computation engine, the architecture of the software that's going to run. A curiosity about how these things work. Whenever a new technology appears and I'm asked to be involved with it, the first thing I want to understand is the information flow and how the system is going to be used and how much data is expected to move back and forth. And if they don't know that, I try and work with the designers to understand the amount of data that's going to be involved, the amount of computation that's going to be involved, how quickly an answer has to come back based on the computation and that sort of thing.
Okay.
And modeling helps to drive that. And I don't think that's any different from the way operations research was practiced before the advent of computing on what was then believed to be a massive scale in the late 1960s and early 1970s. I don't think anything has changed. I don't think the basic principles of modeling have changed.
Then I have another question.
Yes.
Based on years and years experience in modeling, can you give us an example of a project when, from your point of view, modeling was very useful and as a result, project was successful?
Let me give you an example of how I use modeling to justify an invention. Okay. In the mid-1990s, there was an article in a trade journal about how a network management system froze when there was a failure of a massive routing device. The problem arose because the network management system didn't allow more than 3 poles to be unacknowledged at any one time.
Okay.
But it took 2.5 minutes to detect that the system was down, because the way you declared the system to be down was that it would be unresponsive. Mm-hmm. And the timeout intervals, you had 4 chances, I think, and the length of the timeout interval increased in geometric progression from one timeout interval to the next. So you added them all up, you got 2.5 minutes. And this meant that the network management system was frozen, waiting for responses from these 3 nodes, all of which were beyond the router that had failed, for example. And I thought, this seems rather silly. Why are they only allowing 3? And the answer was to keep the network from being flooded with pings that were used to determine the status of remote nodes. And this works just fine as long as you don't have a major failure anywhere in the network that's being monitored. I thought, well, why are they doing this? They're doing this because they don't have a good way of keeping track of what poles are unacknowledged. Except for 3 memory locations that keep track of the IP address of the of the nodes whose poles are not acknowledged yet. I thought, well, why limit ourselves to 3? Let's have an arbitrary number, and let's use a hashing mechanism or some other kind of indexing mechanism to rapidly find the unacknowledged poles whenever a timeout occurs. And I filed an invention disclosure, which eventually turned into a patent. And one of the supporting materials for that I came up with was a very simple model of how long how long one should wait, and how many unacknowledged polls could be outstanding at a time, and how long you'd have to wait for a response from a node that was actually alive. If the node's dead, you're going to declare it dead after 2.5 minutes anyway. But you don't want to wait 2.5 minutes for an opportunity to find out the status of a node that's live and responsive.
Okay.
So I came up with a very simple probabilistic model to figure out what the amount of time would be to send the 10th poll, the 20th poll, the 3rd poll, the 100th unacknowledged poll. So it wasn't a queuing model at all. It was just a very simple recursive model that said I have this many in front of me, and the expected time I have to wait for the unacknowledged messages in front of me is thus and such.
Okay.
And then I did a curve contrasting what the expected time would be with the original scheme.
Did you have service level goals?
No, I just wanted to get the message through. Okay. I just didn't want the network management system to be frozen.
Okay.
And if you think about it, you have a router that's failed with 100 nodes that are only reachable through that router.
Okay.
Okay? And you can only poll 3 at a time.
Okay.
Okay? So you have 100 over 3, which is 33 and something, multiplied by 2.5 minutes. That's an awfully long time for a network management system to be frozen.
Right.
And if you had effectively no freezing at all, then that was a success.
Okay. Okay, good. So
And
did you get a patent?
I got the patent. It was my first patent.
Congratulations.
I think it was in 1997 or 1998.
And Andrew, if you think about new generation of scientists and practitioners, and somebody would like to be involved in modeling, okay, what would be your recommendations? What he should start with and to be a successful modeler?
Well, first of all, I think we need to define success. And
maybe it's another question. How would you calculate return on investment in modeling?
Well, coming back to the network management example, we'd have to think about what the value would be of certainty of knowledge that the remote nodes were actually functioning.
Okay.
If the network management system were down for a very long time, what would the cost be of manual intervention to go and find out whether those remote nodes were truly down, or whether it was some other router or articulation point in the network graph that was down?
It's clear. What if we're talking about computer systems and we're talking about software performance engineering or capacity management? How would you calculate return on investment in modeling? Modeling takes time, efforts, and if company is buying modeling packages, it's another expense. So how people should try to estimate return on investment in modeling efforts?
I think it's best to focus on the cost of the modeler rather than on the tools.
Okay.
Because systems have now become so diverse that a classical modeling tool may not be helpful.
Okay.
So one should think about the return on investment of the modeler's skill.
Okay.
Which
very expensive.
It's over the course of a year and the amount of time it takes to build up the experience base, it's very expensive. In terms of the hourly cost invested in answering a question, it's not so expensive.
But I think
compared with the return on investment,
intuitively, I think we understand this part. But how to calculate positive impact of modeling results? How we save money by doing modeling? What will be your advice? How to calculate savings?
Well, I think one should focus on loss of revenue, because there are plenty of studies out there that show that if the response time of a website is too large, people are going to jump to the competition.
Okay.
And if people keep on clicking on a website because they can't go anywhere else, they're a captive audience because it's a financial transaction or something like that, you need to think about the cost in terms of lost goodwill, but also in terms of running a call center to have someone intervene manually to make sure that the transaction actually went through.
Okay.
So you'd have to calculate the cost that way.
Okay. So,
and if your system is more responsive and you need smaller call centers for manual interventions, that's a direct saving.
let's use your proposed method of calculating return on investment in modeling as a mechanism of evaluating success in modeling. So if somebody start thinking about modeling career, and success, it means increased return on investment. What he or she should start with? What will you advise? How to be involved in modeling? And success, as you defined, is basically reducing losses and
in the examples that I've cited, yes.
So this
another example would be shortened time to market, because
Okay.
if the system functions badly on performance test,
So that's your criteria of success.
a shortened time to market or a shortened cost associated with poor system performance.
Yes, so your criteria, okay? And somebody is going to start career in modeling. What will be your recommendations? What he has to
Stick to the basics first of all.
okay?
Modeling and performance engineering at the highest level draws on many disciplines. It draws on statistics, it draws on queuing theory, it draws on simulation skills,
Okay.
So general operations research,
Okay.
but you also have to have a very sound grasp of how systems function.
Okay.
So I would recommend that someone study operating systems, take a very detailed course in operating systems actually. Not just how one operating systems work, but the principles of operating systems. And the reason I focus on the principles is that there are many different operating systems, but they all run into the same kinds of problems. You have to worry about process management, thread management, concurrency and control, memory management.
Okay.
The technologies change, but oddly enough, the basic problems don't change.
Okay.
So I would say get a very good grasp of how computer systems work, get a good grasp of how computer networks work,
Okay.
acquire the ability to understand new technologies as they come along,
Okay.
be prepared to study very quickly things that you know nothing about,
Okay.
and
Model uncertainty.
No, I don't mean that. I mean that when a new technology comes along, you need to understand how it's put together.
Okay.
You need to understand roughly how measurements are gathered to make sure that the measurements that you're gathering are sound.
Okay.
And you need to understand basic queuing theory and statistics so that if you see, for example, a performance monitor
Okay.
that gives you disk utilizations that are in excess of 100%, you're skeptical about it.
Right. Okay. Well, that's quite a few things. What about the importance of understanding business processes and how it's related to modeling? What are your thoughts about that?
Well, I'm rather biased because I didn't study any of that stuff at university.
Okay.
I learned it by experience.
Okay.
And that's where the curiosity comes in. You want to be curious about it. You want to be prepared to talk to people who are involved in these business processes, but you also have to learn how to explain what you're doing to people who have no reason to understand what you're doing. One of the speakers at the conference today said that he was explaining DevOps to his parents. He felt if he could make his parents understand DevOps, then he could make anybody understand DevOps. And actually, I have had similar experience. I tried to explain things to my parents. And to friends of mine who might be involved in law or economics or something like that and not know anything about computer systems or mathematics and statistics at all.
Okay.
But I've had people working with me as performance engineers who had very good intuition, but one of them was trained in theater and some were trained in music, and I think that's very interesting because as an amateur violinist, I learned very quickly that when you're setting up a concert, you have to do a lot of preparation. You have to make sure that you have the right number of music stands on the stage, the right number of chairs. There's also the rehearsal.
Well, I didn't know that you have experience in music. So.
Yes. I was a very serious amateur violinist for a long time.
Oh, so you're competing with Mike?
No, I'm strictly classical. Mike is a jazz violinist. But and the theater guy with whom I was working, understood about test preparation because I explained to him that you had to arrange the furniture on the stage and describe where people were going to move across the stage and how they were going to leave the stage and when they were going to face the audience and where they were standing next to each other. And the relationship between this and performance engineering is timing.
Yes.
And he got it, actually.
Yeah.
He got it.
Yeah. Amazing. Andrew, it was interesting discussion. Thank you very much for sharing with us your ideas and experience in modeling. And I didn't know that you're a professional musician.
Not professional, but very seasoned.
Seasoned musician, and actually it helped with your modeling career.
Oh, I think musicians have a very good understanding or potential for understanding concurrent programming.
Okay.
Because they understand different lines going on at once.
Yeah, rhythm and
they understand rhythm, but they also understand synchronization,
yeah.
and they understand non-determinism.
Yeah. Thank you very much.
Thank you.